This is a panel on data and methods. We have 5 presenters today. I'm very excited to hear all these papers. I looked at the slides last night, and I'm a little bit disappointed in some ways that there's a lot of you here because I have a lot of questions for the presenters, but unfortunately I won't be able to monopolize the time. So I'll introduce the presenters, and then a lot of the papers have co-authors. I'll let the presenters introduce their co-authors if they wish to. The presenters today, so our first presenter will be Hannah Postel. She is an assistant professor of public policy at Duke University, and she's a faculty affiliate at the Duke Population Research Institute and the Stanford Immigration Policy Lab. She holds a PhD in demography and social policy from Princeton. Our second presenter will be Torben Johansen. He is an assistant professor in econometrics and data science at the Department of Economics from the University of Southern Denmark. His research focuses on causal inference and data science, and in particular on using methods from machine learning to answer questions regarding the importance of early life conditions and policy evaluation. In his research, he uses machine learning for data creation from historical documents and causal machine learning. His current projects include research within the development of new methods for data creation and empirical analyses of health intervention programs. Our third presenter will be Christian Vedel. He is an assistant professor at the Historical Economics and Development Group at the Department of Economics from the University of Southern Denmark. He is interested in how geography and institutions shape living conditions and does most of his work using techniques from causal inference and machine learning on large amounts of historical and/or georeferenced data. Our fourth presenter is Kelsey Carlston. She is an assistant professor of economics at Gonzaga University in Spokane, Washington. She's interested in the geography of intergenerational mobility and its connections to longevity and health. The work for this presentation was largely funded by a diversity supplement from the National Institute of Aging. And our final presenter is right there, Miguel Talamas. He's an economist at the research department of the Inter-American Development Bank. He holds a PhD in managerial economics and strategy from the Kellogg School of Business at Northwestern University, and his research focuses on gender gaps, labor markets, and firms in developing countries. So those are our presenters. I'll let Hannah start. Presentations will be 13 minutes, so I'll be keeping time.
Great. Thanks so much, Matt. Thanks everyone for being here. Some jokes going around about having methods first, but hopefully we can keep you all invested. This is some co-authored work with Abramitzky, Leah, Boustan, and Katherine Eriksson. Luckily, a lot of people over the past couple days have given really great introductions to record linkage, and so I'm kind of going to zip through this and just sort of add on a couple points to sort of the great foundation that's already been put out there. So as most of you know, I think, doing historical record linkage enables us to study important topics like intergenerational mobility and immigrant assimilation that wouldn't be possible unless we could link records. And this is a particularly challenging prospect in historical data because unlike in the modern day, which is still very tricky to do record linkage, we don't often have unique identifiers in historical records. And often, since there's been such a boom in the linkage and production of historical data over the past number of years, including primarily here, we've gotten a lot better at linking entire populations. And so often we assess how well these automated linking methods work by analyzing both match rates and accuracy of the entire census population. But what I'm going to be talking about today is that these measures, both match rates and accuracy, vary substantially by population subgroups, particularly for immigrants and racial minorities. This means that there's lower match rates and lower match accuracy. And so I think the biggest takeaway from this presentation is that if you're working with a population subgroup, please, 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 please don't just download data and use it as you download it. It really requires some extra effort to make sure that the links you're using are accurate and sort of well-made. So this project aims to understand why certain subgroups might be more difficult to link than others and to take some steps towards providing solutions here. So as we've sort of gone over, I don't need to spend too much time on this. There's sort of 3 major camps that have been producing these major automated links in historical data. So there's sort of 2 different approaches. The first is fully procedural. So this is the Census Linking Project, as Trent was talking about yesterday during lunch. So essentially, this is a fully automated algorithm. You take various inputs from the census in this case, so first and last name, age, place of birth, and there's sort of 2 different ways that the Census Linking Project links people basically by how how exact you want to be on somebody's age. But essentially, you just take those inputs and you see who the computer finds as being a good match for that. And then MLP housed here and the census tree at BYU are using more machine learning type approaches. So by providing training data, which for the census tree at BYU is hand genealogical links made on the family tree on Family Search, they use machine learning algorithms to learn from the training data and produce a wider network of links. So before I move forward, I'm going to say this presentation is not about which method you should use. I think as many people have said, and I totally agree with, all of these methods have pros and cons. And really, if you're doing research, you can think about sort of which of these trade-offs is most important for your research. So one thing I will say before I show this next figure, which has a lot of numbers, is I'm going to talk about sort of the common trend I want you to see in these numbers, and then I'll talk briefly about some of the pros and cons of these different matching approaches, but that isn't going to be the focus moving forward. What I really want to talk about is how all of us who are working with population subgroups can work with those data to produce better matches and to do inference on our data. So there's a lot of numbers here. What I really want to call your attention to is just the trend down the chart, right? So here's native-born whites at the top. So this is the conservative version of the Census Linking Project, MLP, and the census tree. I'm going to say before we look at these particular numbers, I'm being a bit unfair both to the Census Linking Project and to MLP. This is the old version of MLP, so I'm looking forward to getting into the new links when I get home. But these rates are probably much higher now that they've released MLP 2.0. And then Census Linking Project, this is their conservative matching approach, which basically uses a smaller age band than these other matching approaches. So these two columns are probably lower than some of the data you might be using at home. So basically what I want to show here is just we can see the native-born white match rates at the top, up to 70% for the census tree. And essentially, as we move down this list, it doesn't matter which algorithm you're using, the match rates fall off dramatically. And so this is just to say, the native-born white population is the majority of the census population, but when you really start looking at these smaller groups, we're really not doing as well by using the algorithms that we are using. The only thing I'm going to say about census tree here is that most of their training data is based on these native-born white individuals. The training data for individuals in these groups is scarily small, like could be dozens of people, could be hundreds of people. And so I really just want to urge caution that even though they have relatively high match rates here, most of these are produced by their machine learning algorithm, which is training on a very, very, very small sample and is thus mostly learning from individuals who do not actually look like this target population. And so I would urge you, if you want to use census tree data for population subgroups, to really use only the hand-linked family tree data and to carry some healthy skepticism about the machine learning links made there. Some of them are too small to use just the hand links. I think for Chinese immigrants in this year pair, they only have 19 individuals or something in their training data. But I really want to highlight that here, and that's no shade against census tree, but it is something that's very, very different from these other matching algorithms, and I think should be talked about more broadly. So really what I just wanted to highlight here is this differential across all the algorithms down these population subgroups. So why might subgroups be more difficult to link? It's totally possible that there could just be a lower ground truth match rate for these subgroups. I think one of the main challenges in doing these linking is we don't really know how many people we expect to find year to year, and we may expect to find fewer members of these subgroups over time. That may be because we know that return migration rates were high during this time period. So if somebody left in an intercensor period, we should have no expectation of finding them. Just some illustrative evidence here. When I look at Italian match rates in 1900, 1910, I showed you they were the absolute lowest group, like 4.4% matched by the Census Linking Project. Their match rates in 1930 and 1940 are 184% higher. And this is because the migration in earlier periods was much more circular. People came for shorter periods of time and returned home. And then later in the 20th century, people were staying put longer. And so this is sort of some indicative evidence that return migration may be playing a role in these very low match rates for immigrant groups. The other thing is perhaps higher mortality. So many of these groups, both racial minorities in the US and immigrant groups, may have been employed in riskier occupations. They may have lived in neighborhoods with worse sanitation, et cetera. So they may also be dying at higher rates than the native-born white population. And that's another reason we might find it more difficult to find them in the census. There's also some particular things about some of these groups that even though the ground truth match rate might not be lower, like even if we expect to find the same share of people, there are things that are going into our algorithms based on what our algorithms make matches based on that could make linking these groups harder. So that could be heaped age reporting, so non-native English speakers or people who perhaps didn't have literacy numeracy as high as the native-born white population, often rounded their ages to 5s or 0s, and that could make it more difficult to find people over time. There can also be group cohort effects, so sort of about the age reporting. I think we know that Native Americans, not Native Americans, I'm so sorry, that Black Americans who were born before emancipation were less likely to be literate or numerate, and there may be more issues with age reporting with people who were born before emancipation as opposed to after emancipation. And also naming conventions, which I'll talk about later. A lot of our algorithms rely on both the segmentation of names that follow English language conventions, as well as some cleaning algorithms that employ methods that are based on English. And so all of these things may make it more difficult for these groups to get matched. So we're just going to do a very, very quick back of the envelope estimate to try to understand if subgroups have a lower ground truth match rate. So we're just going to take, this is my ostensible demography training, take the 1900 population, ostensibly fast forward it to 1910. We're going to exclude births in that period. We're going to exclude immigration in that period. And so the share of the population that's remaining is an estimate sort of the population minus deaths and immigration. And we're working on more formalized return migration estimates because you could imagine that the population size might remain the same, but those might not be the same people. So we're working on incorporating that. And so essentially what we find here, you can think of just the percent found from one year to the other. You can think of native-born whites. So this sort of says that about 10% of native-born whites either died or left during this period by this back-of-the-envelope estimate, and that it's lower for essentially all of these other groups. So this suggests that the ground truth match rate for these groups actually may be lower because more of them died or left during this period. And so here I'm just scaling up that census linking project rate, and you can see that for English immigrants, for example, who had sort of more churn during this period, we're starting to approximate the native-born white match rates here. So this is just to sort of give an understanding of how much is due to what was actually happening on the ground historically during this period, as opposed to sort of some of these algorithmic challenges. So how can we improve subgroup linkage beyond sort of this back-of-the-envelope estimate? As I mentioned, there's some algorithmic challenges for people who are born overseas. We only have their country of birth, which is not very granular at all. There may be low uniqueness by people's name and age, just based on how how those demographic trends occurred. And there's some issues with names. So everyone deals with transcription and enumeration errors, but this is particularly challenging for some of these immigrant groups or racial minorities. There's more name changes, people Americanizing their names. And as I mentioned, these phonetic standardization algorithms are designed for English. So we have two recommendations here to improve record linkage for some of these groups. So one is adding extra information to resolve low levels of uniqueness. I'll show you this in a second. And the second is to conduct specialized name processing, particularly for some groups. So here I'm just going to show you this is the level of uniqueness by exact name and age. So these are the people that are completely unique based on name and age. And you can imagine in a lot of these record linkage algorithms, if you are not unique, you are dropped, because if there are more people that look exactly like you in one census year, how are you ever going to be able to know who you would match to in the next census year? So I want to draw your attention here that only 60% of Irish and Swedish immigrants were actually unique on name and age. And so this makes it essentially impossible to find at least 40% of them. And so what we do is we add extra information to break ties to distinguish between individuals who previously looked identical. So I'm not going to go into this. This is sort of what Trent, talked about yesterday. So there's new links from the Census Linking Project that add extra information like MLP and Census Tree have been doing to break ties and be able to make more links. And so this is just showing The blue bars are the basic linkage, and then the purple bars are with the extra information. You see match rates go up for every group, and they particularly go up. The dotted line is the percent change from adding the extra information. And as we would expect, the particularly non-unique groups were able to break those ties and match a lot more of them when we add that extra information. And adding this extra information also enables the use of phonetic standardization algorithms. So I used to say never use Census or other sort of phonetic algorithms for immigrant groups because it actually introduces more errors than it solves. But I think adding this extra information, because we're more able to granularly see what's going on with some of these individuals, I would say now only with the conservative specification of the linking project and only with this extra information, adding Census actually doesn't decrease any accuracy and increases match rate still. And particularly for these groups that had high uniqueness, probably inflated uniqueness due to misspellings and things like that, this is where a standardization algorithm like Census helps. And I took too much time at the beginning, so I'm just gonna blast through this here. There are some groups like this shows, the Mexicans and the Italians are really still lagging here. And so what we recommend for these groups is to do specialized name cleaning for these groups. So there's more name transcription. It correlates with uniqueness, as I mentioned. Names aren't organized the same way. So typically we match first name to first name, last name to last name. Hispanics, for example, have multi-part names that may be misorganized and hard to link under our current framework. This is drawing on some previous work that I'd done for Chinese immigrants, where I looked at how names were split apart, how they were ordered, and how they were standardized, fixing those things in line with sort of linguistic characteristics of the Chinese language, but raise both match rates and accuracy. And so we're doing some standardized name cleaning based on some previous work. Italians are our bugbear right now. I think some of you have heard me talk about this. We've tried basically everything, really not helping us. So if anybody has ideas about Italians, that would be amazing. And just to conclude, we're finding both lower match rates and accuracy for these groups. For some of these groups, it is a lower ground truth. For some of them, it's not. We want to add extra information. We want to conduct these specialized name processing. And I would just, again, urge you to really look at these groups individually if you're working with population subgroups. We are working on publishing new links. And there is also work today for these racial minorities showing that even when we have more unique identifiers, these name-specific and group-specific differences are still really important. So thank you.
Good morning, everyone. So happy to see you. My name is Torben Johansen, as Matt already said. This is a joint project with Sam and Munir from UBC and Christian, who's also from University of Southern Denmark like me. This is a project where we do something that's very, very simple. We don't do anything fancy on how do you perform linking. We just look at what is the impact of what you put into your linking algorithm. So this is something Hannah mentioned as part of her talk. What is the role of transcription errors? So if we have a name that's just wrongly transcribed in the first sentence or in the first case, what impact does that have when we perform linking? And this is everything I'll talk about. So in that sense, it's a very, very simple presentation. So don't be scared about machine learning stuff. This is just what we do to actually try to get better names. I think motivating this project in this audience, that's probably quite easy. Most of you probably care about linked data sets. We haven't heard a lot of presentations not using that. And also most presentations were using US Census data. We also use that in this project. With that said, I mean, there's nothing in this project that's sort of restricted to US censuses. I want you to think of this project as like, this is just maybe a cautionary tale of one of the things you should think about when you do linking, and we illustrate that using US Census data. It's also applicable to other projects. This is a US Census record. Probably most of you have seen one before, and we focus on this column with names and ignore everything else for now, at least. Maybe once we get this project a bit further, we'll do more than that. So that's everything. So essentially, the question we set out to answer is there's some evidence that names are transcribed wrongly a fairly high amount of time, at least to some extent. So if you look at human transcriptions of US censuses, and you have two sets of transcriptions of names, around a quarter of the time, the two humans will disagree on the name. So it's a fairly large share where there's at least some amount of disagreement. And we try to provide better transcriptions, and then we look at what does that do to our linking in terms of how many we can link, and also in terms of whether those links perhaps are hopefully also better links. And in this paper, I'll be talking about the 1930 and 1940 US Census, where we sort of operationalize this. So there's a lot of literature on linking. There's a lot of literature, especially on, so I've tried to split it into two different streams of literature. There's the algorithmic improvements to linking, and I'm not doing anything there. There's a lot of great work, including by people in here, on how to do that. Then there's much less work, but a bit coming out. For instance, my co-author in this project, Sam and Munir, has a couple of projects where they look at trying to see what impact wrong name transcriptions have in terms of who we can link. And this is what we're extending in this work. So we use the full 1930 and 1940 US censuses. We retranscribe everything in there. So the data-wise is, well, I mean, the full censuses, all the images. And to sort of do this and to illustrate the impact, we also use the transcriptions done by both by ancestry and by family search. And we look at two different groups of names. We look at names where ancestry and family search agree, this is the same name. And in this project, we're going to be treating that as this is like the gold standard. I mean, I'm not saying this is true all the time. This is what we imagine in this project. This is the truth. And then when that's not the case, a quarter of the time, these are the records that we're going to target and try to do better on. This name is one where ancestry and family search agree. They both say this is James W. Salvatore. And this is another image, and where they disagree. So they disagree on the first and the last name here, although only slightly. So depending on your matching algorithm, this difference I'll show you here, whether it's Antonia DiBiase or Antonio DiBiase, it might matter, it might not matter, depending on the algorithm you use. So sometimes it's these small deviations, sometimes it's larger deviations. We're going to be using the first set of images to train a machine learning model to transcribe the remaining 25% of names where these two organizations disagree. And then we're going to be using linking, just using a very standard approach, and we're going to see what happens. So the way we transcribe it, I won't spend too much of time, but I love talking about transcription, so you will see a few figures. This is just a figure from one of my other papers in historical methods, where we think of sort of transcribing these large tabular documents or collections of tabular documents as a three-step process. We have a diverse set of documents. We want to classify which is which. This is really easy here. It's just US Census records, everything. It's nice and simple compared to a lot of other projects. And then we're going to cut out these small images from the record. So this could be a specific name in a US Census, and then we're going to be transcribing that. How we segment these fields is what we are doing the most different compared to most other studies. So we are using a method where we don't train any model to do this segmentation. There's no training on US censuses here or anything. We're going to be exploiting the fact that it's a tabular document. It means it's going to have straight lines. Some are vertical, some are horizontal. We're going to be looking at the intersection, and then we're going to drawing a lot of points on all these intersections. And we're going to use that to fit a model, a maximum likelihood estimation problem of trying to map these points from one image into another. So essentially, I'm going to go into the 1940 US Census. I'm going to pick out an image at random, and I'm going to manually draw in the line, but I'm going to do that just once. And I'm going to call this a template image. And then on all other images in the 1940 US Census, I'm automatically trying to find the lines, the vertical and horizontal grids. And then I'm going to fit a transformation function that transforms all the other images in a way to look like my template. If I can do that, I know where everything in the record is, and I can extract all the fields, and that's very neat. So those of you with a keen eyesight might be able to see some blue dots here, hopefully. This is what it looks like. This is a half page of US Census. These are the intersection points. Those of you with very keen eyesight might notice that, for instance, down here, some of the dots are missing, we don't identify everything, that's a total non-issue. These algorithms are very, very robust to not identifying everything. So we don't need to do that. And this leads us to be able to segment more or less all the fields of all the 1940 US Census. We're working on the 1930 US Census now, doing the remaining of that. And then we can put some bounding boxes and extract the individual names. All right, that's everything about transcription or about segmentation. Then we retranscribe the fields. So we just use a database of handwritten names and we supplement it with these where family search and ancestry agree. We pretend this is the truth. If we do that and transcribe, we get a fairly accurate model that correctly identifies around or slightly more than 98% of the characters in these names. So fairly high transcription rates. And if we then go back to this image I showed you earlier, just to illustrate that what we do isn't just always copying family search or ancestry, which you might worry, is it just that one is always right? That doesn't appear to be the case. So just this example image here, we actually end up with something that's like a bit of a mix between those two. Okay, so as I alluded to earlier, ancestry and family search disagree. Now, so far I've talked about the full 1930 and 1940 US Census, and now I'm dialing back because we're not entirely done with this project. So now we're in Rhode Island, which is not as exciting as the full one, but those of you going to SSHA, this is our deadline for having the full exciting stuff. So hopefully in Chicago you'll see it. Thank you. So just to illustrate here, so in 1930, around a quarter of the time, these two organizations disagree. It's 30% in 1940 where they disagree with each other. And when we retranscribe it, some of the time, 16% of our time, our model will agree with ancestry, 42% of the time with family search, and 42% of the time with neither of these organizations. So these are truly new names that are put in. We're doing something for now very, very simple. We're working on extending this. We're just using a very conservative ABE algorithm for linking. There's not much magic here. This allows me to get some really dramatic numbers to show you because it's so conservative. I think it's fair to say if we use more flexible, it'll still look like something that matters, maybe not exactly as much. As a baseline, I'm using the ancestry names, and we're doing linking. And then as a post improvement, I'm replacing the ancestry name where ancestry and family search disagree with each other. I'm going to be reporting three different things. I'm going to be looking at the linkage rate. I'm going to get some idea on the quality of the links. I'm going to be looking at when the middle name initial is available, how often does it match. So we don't use this for linking, but presumably if links are better, more of the time when the middle name initial is there, it should match between the 1930 and the 1940 name. And then finally, for some groups and some areas, Hannah also alluded to this, things are more difficult. That's also the case with transcribing these names. There's a lot of heterogeneity in terms of how often does family search and ancestry agree/disagree with each other, and that varies a lot. So we also going to be looking at when legibility is very low, does this have a large impact? Yes. All right, so if we look at our target records where family search and ancestry disagree with each other, if we use our revised names, we improve linkage rates by 147%. So this is fairly large. And this is not just, we hope, a lot of new false links. If we look at the share of observations where we can validate the transcript or the link by middle name initial, that actually also increases by 38%. So we get, 150% more links that appear to be of higher quality. So this is the sort of the punchline of the presentation. And the last three figures I'll show you are just some heterogeneity analysis in terms of where does these additional links actually come from. So what this figure shows is on the x-axis, the pre-improvement linkage rate. So before we revise the names, what is the linkage rate? And then on the y-axis is what is the increase in linkage rate. And more or less across the board, we see a higher linkage rates. And more or less across all groups, this is more or less because for some reason inmates, we do really, really poor on inmates. So those are worse, but every other group, we get a lot of additional links. So we get more links across the board. And this is, of course, perhaps particularly interesting for these groups down here where linkage rates are very, very low to start with. So the relative improvements here are very large. If we look at how many of the links we can validate by middle name initials, this is also an improvement just across the board, aside from these inmates who are really weird for some reason. So we also see that we appear to obtain higher quality links for more or less everyone in this 1930-1940 US Census. And finally, where this is particularly concentrated are the cases where family search and ancestry really just disagree a lot with each other. So on the x-axis here, we have the legibility, and our legibility measure is what share of observations in an enumeration district does family search and ancestry agree or not on. And we can see that the red dots here, this is before our improvements. This red dot jumps up here. So particularly for groups where transcription is very hard, legibility is very low, this is where this really matters. And that could be something that matters more for your study depending on what you focus on. Okay, so to wrap up this talk, we do something that's really simple. We just look at what goes into a linking algorithm and what impact does that have. It turns out to have an impact. The results I've showed you, those are just Rhode Islands. Those of you who've seen this talk before, it's not because we don't do anything, I promise, even though a lot of you saw this talk in March. We are actually working on it. We are done with 1940 now, but working on 1930. So the other state stuff is going on. Of course, it would be great also, and this is something we're also looking into, more flexible linking algorithms, because some linking algorithms are probably better at dealing with some of these mistakes, but perhaps not others. Then we are talking about, but we're not sure we want to pursue this, of looking at other fields than just names. Names are just the hardest one. And potentially we could also do this for other census years. At a certain point, there's also like a computational infrastructure aspect of doing this, but potentially that's also interesting. Thank you.
Brilliant. There you go. My name is Christian Vedel. I am not the same Christian as Torben mentioned before. I did not take part in that at all, but that other Christian is also part of this project up here, and Torben is also on this project. But this is I'm this Christian down here. So everyone at our university is called Christian for some reason. It's really weird. So I am here to present this project that we've been working on for a while, and sort of to level expectations from the beginning. We are not really contributing any new insights here. What we are doing is taking a completely trivial solution from the machine learning literature, and then we're applying it to a problem in historical data. And that is all that I will be showing you today. So, in economic analyses, we often require information on individual level occupations. And often what we want is to have neat boxes to fit things into. So one example of that is sort of the HISCO system. So you would want sort of to be able to describe individuals' occupations as in sort of terms of digits. So this is a geologist, and if you then have census data, for instance, with these particular standardized codes, then you can just count all the geologists. So the problem is that often when you look through historical data, it does not come with neat codes. It comes in this form. And I mean, that's not very neat. And it's very hard to count the number of policemen or the number of farmers when it's all mixed up with these type of strings. What we want is something like this. So a standardized code for a gunner in the Royal Artillery and so on. Luckily, there's a nice little system developed some 20 years ago to classify historical occupations. So before I showed you an example with the HISCO system, if we add an H in front of that, then someone has worked out how to do that with historical occupations. And it sort of has the same nice structure. So sort of the first code describes sort of the overall sector Then the second code describes some more specific information, and eventually we end up with a very specific sort of category, and then we can end up counting all the farm servants in some data. So the problem is generating these HISCO codes, or any other type of classification system for that matter, requires that you sit down, read and understand and comprehend what occupation lies behind that description. And that's a lot of manual work. And if you have millions of observations, then even if you can do one of these in 10 seconds, and if you're good at it, you can do one of these in 10 seconds, it still takes hours or days of endless work. Then, of course, what you could do instead is that you could use regular expressions or sort of tools from the old NLP box, the toolbox, so you can sort of match up things with similar descriptions, or use variants of string distance and so on. But the problem is when you've solved this for one particular source, then your solution does not generalize. So what we do is that we train a neural network, which is faster, more accurate, easier to use, and also fully replicable. So once you used our solution once, you can run it again on another source, and you get similar results because it works the same every single time. And you also save a lot of RA hours. So all this is possible because of a lot of very generous people out there that have either publicly made their data available to us or explicitly shared data with us for this project. In total, we collected 18.5 million observations, which contains an occupational description and a standardized HISCO code. And I mean, it wouldn't be possible to do any of this work without what they have done. So we are essentially taking all the manual work that has gone into solving this problem and turning it into an automated solution. And we end up with data on 13 different languages, and for that reason, also something that works in 13 different languages. Here's a very, very simplified version of what the model does. You input a language, in this case English, and then you input some occupational description. You can also leave the language out, then the model can sort of guess from the description what the language is implicitly, and then you run it through our neural network here, and what you get is then the appropriate HISCO codes. So this is the HISCO code for a farmer, this is the HISCO code for a fisherman, and so on. Please ask questions if you want more details about how that works. In practice, what it is that it's a transformer model, so the same type of model that powers ChatGPT, but this is not one of the sort of big transformer models. This is a small transformer model, so only around 100 million parameters. This also means that you can run it locally on your own computer. And the neat thing about this particular model that we use, called the OccCANINE model, is that it's character level. So occupational descriptions are often very short. So that means that even with spelling mistakes and transcription errors and so on, we can still just input all the information. And if a human can guess it from the context, then our model should also be able to guess it. Then, of course, to get something that really works for these sort of things, you have to make the life harder for the model. So what we do is that we randomly insert text into the training data. We sort of delete characters. We also translate things to different languages and then back again and so on, all in an effort to make sure that what we develop is something that also generalizes. And here's a bit of a technical thing that we also had to solve. And I mean, the reason I'm including is because we often get questions relating to this. And the question is often, well, I mean, can you generate more than one code if there's more than one occupation? And yes, we can. But to be able to do that, we had to solve this problem of order invariance. So I guess that's a small but neat little contribution to the machine learning literature as well, that we have developed this loss function, which gives the same amount of points if the model guesses farmer and fisher as if it guesses fisher and farmer. All right, so how well does this work? Here's just the baseline test split performance. So this is data that the model has not seen in training at all. And then we run it and see how well the model predicts the HISCO code of those descriptions. So the baseline accuracy is 95.8%. And then, of course, if we add in some context, in this case, just the language, we get slightly better performance. It also works surprisingly well across a number of different languages. This is just all the languages that we have. You will notice that we don't perform very well in German. So if you happen to have some German training data, then please write me an email. But even for German, we're still sort of in the 90s in terms of accuracy. Then, I mean, all this is sort of based on data where we had a very where we had a source, and then we took some of the information from the source, and then we tested it on that. What sort of happens in real life is that you have something completely new that you want to use this on. So we try to sort of test that by taking two entirely new sources that has no HISCO codes on them, and then we try to predict the HISCO codes and assess its accuracy. So these are the Copenhagen burial records, which are burial records, and then it states people's occupation when they died. And these are Norwegian student biographies, biographies, and then they state the father's occupation. So we run our model on that, and then we walk over all the predictions, and then we sort of assess whether it's accurate. And for sort of substantial agreement, we are around 95%, and for full agreement, so sort of a very strict sense of agreement, we are still close to sort of 90%. We also test whether this method would work for other systems. OccCANINE, that's the UK census system of classifying occupations, historical occupations. The OCC 1950 system is used widely in the American census data. And HISCO 68 is also one of these type of systems. And for all of them, after a bit of fine-tuning, we can get pretty adequate performance. Of course, it seems that there's still some tweaking to do for this particular system. But I guess 85% is still pretty good. All right. So usually I like to demonstrate this because, I mean, it all sounds kind of fancy. So usually I would bring my laptop and then I would demonstrate the code live for you. I can't really do that here. So I've done something else. I've sort of cheated. So I recorded the demonstration in my hotel room yesterday. That also makes it so much less exciting for you because you know that it's going to work, and it would be so much fun if my code didn't work. But I promise you this actually does work. So what we do is that we load up this little library that we made in Python, and then we load some data. Here's just some toy data with 10,000 different occupational descriptions. Yeah, there it is. And then we load up this model, OccCANINE, and then we run the predictions. And I mean, it takes a few minutes. I'm not going to keep you here for a few minutes. In a moment, I'll speed this up. So yeah, there you go. So now it's sort of, I mean, now I'm cheating, I guess, but it's still relatively fast. So there you go. And after waiting a couple of minutes, then suddenly you have HISCO codes, standardized HISCO codes for 10,000 observations. It took 2 minutes and 21 seconds. And if a human could do it, they would have used 27 hours on doing the same. So that's pretty neat. And it also outputs sort of a confidence score on how confident you are for those predictions. All right, so just to wrap things up, we develop and make available this model for classification of occupational descriptions into standardized systems. And when I say available, then I mean you can go and use this right now. Everything is freely and openly available. You should probably start with the GitHub, where we sort of document how to do things, and then there's also a YouTube tutorial on how to do things, and there's also a paper out there on arXiv on how everything works, and we test various the elements of the performance. I should say that we really hope to get the new version of the paper out pretty soon. But yeah, we really hope this is useful. That is really what we have been trying to do. So I really look forward to questions when we get there. Thank you so much.
Hello, everyone. My name is Kelsey Carlston, and I'm a professor at Gonzaga University. I'm going to be presenting my work with my co-author he did all the machine learning stuff, so I know it a little bit. But we're estimating using new methods for measuring occupational status. So the historical full count census data is an incredibly rich source of information. We've seen a lot of really cool projects from people at this conference that are using it. And my interest is looking at intergenerational mobility in the life course. And what's nice is these people from the early 1900s, we've seen their whole life. So we know how some of their economic conditions can affect their health across the lifespan. But the problem is that we didn't have income and education measured before 1940. So that poses a challenge to people who want to do economic or socioeconomic status analysis. The current methods that are most commonly used are like you can use occupation groups. So are they a farmer or white collar or blue collar? That's like the most simple. Or there are these occupation-based scores that you can get off of IPUMs, and those are very common, like the OCC score and SEI. But the problem with using occupation-based scores is that I think the biggest one that I was running into challenges with is that like a quarter of people in 1920, and before that even more, were farmers. And under this, they all have the same score. So whether you were like a poor black sharecropper in the South, or you owned a wheat farm in Washington, you would be counted the same, which is a problem overall. And then some of the papers that have come out recently using this data that are in AER and everything are using geographical analysis. And a lot of counties had over 90% of people were farmers. So having one score for those people doesn't really work. So our goal is we want to be able to use the richest data set possible when we're answering questions about the past. And we're going to try to make a socioeconomic status variable that includes all of the available data that we have in the census, rather than just a few like occupation and age. A few people have done creative things recently to try to solve this problem. So one is using combinations of 1940 variables or 1950 variables to predict the income during that census. And those work pretty well, but the problem is they don't work if there are changes in the industry structure. So the relative positions are not the same. So for example, if you were a miner in 1920, you're like in the mines with a pickaxe and planting dynamite and stuff. Whereas if you were a miner in 1940, you're working heavy machinery and you're a skilled laborer. So it's kind of unreasonable to believe that a miner in 1920 would be the same status as a miner in 1940. So other researchers have been trying to find those more contemporaneous variables. So like those two papers at the bottom tried to predict the average or the literacy rate for either each occupation or each occupation and race, something like that, which I think is a reasonable thing to do in the 1800s. But in the early 1900s, what you find is that most of these occupation times race times age categories are between 90 and 100%. There's very few of those that dip below 90%. So there's not a lot of variation that you can use to try to understand relative status. So what we do is we link the 1920 and 1940 census using MLP links. And though we've tried a lot of them, but we're predicting the 1940 income and education using 1920 variables. So we know what they did in 1920 and can use those variables to predict, presumably there'll be some intragenerational mobility, but not a lot. And so we think that can help. Another thing we're doing is we're including all of the variables that the census has available that other studies aren't including. So one that I think it's important is ownership, particularly for farmers. Nativity, were you born in the US? How many children do you have? what county are you in. So including all of those variables allows us to catch more of the variation. And we're using a light gradient boosting machine for prediction. So this is a nice thing that allows you to not only use the giant categorical variables that you're dealing with, like occupation and industry, but also it allows for nonlinearities and allows you to capture interactions that might be important for predicting this, while not still having power in, you don't have too small a categories that you don't have enough people. So when we do this, we find that, okay, the most important variable for predicting socioeconomic status is still occupation. So that's good news for everybody who's using those OccScore variables. But then a lot of these other variables are not being included in measures right now, and they're important as well. So are you literate? Are you from the US, your state, number of children, and those things. And another thing I'm going to point out is that these are the top 3 biggest occupations in 1920. The top is the farm laborers, the middle is farmers, and the bottom is laborers. And within each race and within those occupations, there's still a lot of variation. So there's a lot of variation that we are missing when we aren't considering all of those other factors. So I'm going to go through a handful of comparisons that we did to see how our measures compared to other measures that people use. So those top 3 ones are ones you can get off of IPUMS. It's OccScore, SEI, and ERScore is how they're coded, and they're generally they predict 1950 income or education based off of variables in that time. The 4th one is they used a machine learning model to predict 1950 income, accounting for more variables, but still not all of the variables that are available. And they're doing it just, for that 1950 variation. And then the bottom 2 are both literacy, getting the average literacy by, or literacy rate by occupation and whatever. So what I did is I just, whatever the outcome is, I did a simple linear regression running each of these scores and then our scores against that outcome. So the first one is predicting the 1940 wage income. This is what we trained on, so it makes sense that we did pretty well. But you can see that these others are not doing as good a job of predicting that. Same with education. I mean, it makes sense. These other scores are not meant to measure education, but if you're considering education as a part of status, again, this is what we trained on now. So it makes sense it does well. We don't even have to worry about it. But one thing I do want to point out is when we're looking particularly for Black men, our measure does just as well as it does for the whole population, whereas the SEI and the score that Song uses have almost no predictive power. So if we're interested in studying these disadvantaged groups, then it makes, we probably need to be looking at something that's more, that accounts for those. So this is something trying to predict something that isn't what we trained on. So this is the son's 1940 ink wage with their father's 1920 score. So this is intergenerational mobility. And what you see is that our income score is a much stronger predictor of son income than the others are. So if you're doing something like trying to see how intergenerational mobility has changed over time, there have been big statements made about like whether it's increasing or whether it's decreasing. But if you're not using the right score, you might find, these ones on the right find more intergenerational mobility than our income score does. So I think there's some problems that we probably want to apply this to. This is one where none of them really do well. Trying to find son's death age. It's just hard to explain much of the variation in that, but I do think that there's a potential to try to connect to some health data that will help us understand how, early life socioeconomic status affects your longevity, which is kind of hard to do with a lot of the data sets we have now. The last thing I'm going to do is in 1915, Iowa did a census where they did collect income and education. So we used our model that was trained on the 1950 or 1940 data, and we applied it to the Iowa census and predicted their income and education. And so this is the education one, and ours does a lot better than those other scores at predicting education. However, when we look at income, the problem is we use 1940 data, which wouldn't capture farmers' non-wage income. And since Iowa was mostly farmers at this time, I think we can improve this by switching to the 1950 data, which is what we planned to do by the time this conference happened. But the 1950 data is kind of hard to work with. Don't know if you found it. So some of the drawbacks of doing a measure like this is that we may be capturing variation that we don't want to capture, or removing the variation we want to test for. So like if we're trying to find economic status by race and we're creating a measure that includes race in it and makes the assumption that, or, you know, is, we just might not be able to do that. So we have to be thoughtful about which kinds of questions this can be applied to. We can't test inequality or other things that require knowing the distribution of income because that distribution changes. So you'd need to use other data sources, but for all of these measures, that's true. And then when we're going back in time to like the 1800s, we can't do that linking to the 1940 and 1950. So we're gonna have to figure out new ways, outcomes to train on. But overall, I think that there are a lot of opportunities for making measures like this. So for me, studying intergenerational mobility and the geography of that, I think that could be very helpful, and it requires more information than was collected. So just trying to get all that we can, all of the information we can out of the census will be helpful. And then we might be able to even open up new research topics if we were able to create a reliable enough measure. So our next steps are we're going to use 1950 data to get the total income instead of just the wage income. And hopefully that will improve a few things. And then we're going to try to refine and add more information. So one of the things that's nice about all these new machine learning and AI methods is that we can add in more information in ways that will help us to refine and get whatever, you know, like BLS had all of these things where they got people's wages in the early 1900s, and we can hopefully incorporate that information in to have the best measures possible. And then try to expand it so that we have measures for all of the pre-1940 censuses, and then the idea is that we want to be able to share these measures with other researchers so that they can use them and hopefully get better research going. So I talk really fast, and I'm really good at finishing presentations early. So thank you for listening.
So, hi everyone. Thank you to the organizers, and thank everybody for being here today. I'm very excited to be here and to talk about the undercounting of child mother birds. Accurate demographic and health data is a public good. We use it for our research, and policymakers use it to understand social problems and to address them, to allocate resources. Now, this public good often relies on individuals' truthful reporting, like we see in censuses or in surveys. But what happens when truthful reporting makes them incur in a private cost? One example of this is if you report your actual income, you might lose eligibility to a social program, to a subsidy, or to a conditional cash transfer. Similarly, there might be some things about your life that you're ashamed of, that you don't want to truthfully report. What it's going to lead to is a market failure. We're going to have inaccurate reporting, and the quality and availability of our public good is going to be worse than what we will have expected or what we will be desired. So what is our paper about? We're going to study this market failure in the context of child mother birds, particularly very young age, 10 to 14 years old. It's well documented that childbearing at this very young age is harmful for both the mother and the child, and these negative effects are bigger the younger the girl is in this case. Now, therefore, for this group is for which we need more accurate data. But the problem is that it's also for this age group for which this asymmetric information problem is going to be more pervasive, because it's also for the age group where we will see the social cost of truthful reporting being higher. So what are we going to do in this paper? First, we're going to measure the extent of misreporting. Then we're going to try to uncover its mechanisms, whether if it's social cost or legal cost. And then we're going to have a theoretical framework that is going to be consistent with what we see in the data. And that I won't show today, don't worry. So what's the data we're going to use? IPUMS, of course. We're going to use it for 59 countries and 80 census pairs. And we're going to pair this as well with birth registries from Brazil, Mexico, and the US. What are the methodology? Well, first, let's think of our goal, which is to estimate the extent of undercounting in censuses and birth registries. And this undercounting can take the form of non-reporting or misreporting. Both of those for us are going to be undercounting. Now, while counting in birth registries is straightforward, let me just walk you through how you do the counting of birth in the censuses. So you do this by reverse survival methods. Basically, you look at the household composition, and from that, you back out fertility information. Let me give you an example. If in the 2010 census, you see a 16-year-old mother of a 2-year-old, that means that 2 years ago, in 2008, a 14-year-old gave birth. Now, there's a drawback from this methodology, is that you will only recover a lower bound on fertility, because you can only count births when the mother and the child live in the same household. So to estimate undercounting, what we're going to do is, for the same country, for the same cohort, and for the same year, we're going to compare birth counts from different sources. And these different sources can be census versus birth registries, or census versus census. And let me explain you how the census versus census look like, going back to the earlier example. So now suppose that you're in the 2020 census. And in the 2020 census, you see a 26-year-old mother of a 12-year-old. That's an independent measure of fertility in 2008 of 14-year-olds. So using the 2010 or the 2020 census, you can back out fertility of the same age group in the same year. So let me give you in aggregate how this look. So in this figure, what we have is total births for mothers aged 15 to 24. Each dot is a country, and it's a pair of censuses, the subsequent ones. On the y-axis, you see the birth counts from the first census. And on the x-axis, you see what you will count in a census 10 years later. And as you expect, I mean, there's measures of the same thing, so you recover basically the same number. What happens if you repeat this methodology with births for 10 to 14-year-olds? Then you see a very different story, right? So for 10 to 14-year-olds, you see systematic undercounting in all countries, in all census pairs, that when the girl was 10 to 14, like when she was in her teens or young, she was not counted as the mother. But 10 years later, once she's in her 20s, then she's accounted as the mother. So for the main empirical evidence, what I'm going to do is first, I'm going to compare birth estimates from census, the subsequent census, and birth registries. In the paper, we have this for Brazil, Mexico, and the US. It looks the same for the 3 countries, but for exposition purposes, I'm going to show you today how it looks for Mexico. And then after showing that evidence, I'm going to show you the averages across the 80 census pairs based on data from IPUMS. And the pattern that we see is 2 main things. First, we see that increased reporting with the mother's age at childbirth. So an 18-year-old is more likely to report truthfully than a 12-year-old or the household. And we also see an increase in truthful reporting by the age of the mother at the time of reporting. So for example, if the mother was 14-year-olds at time of childbirth, and she's reporting when she's 18 or when she's 28, we see much more truthful reporting when she's 28. So let's go with Mexico and first start with this 2010 census. So based on the 2010 census, we can get the births of mothers aged 15 to 24 for all the years before the census. Now we can get an independent measure from the 2020 census. And here you should, the main thing is like looking at the overlap. This is 5 years between 2005 and 2009. And we recover mostly the same number. Mechanically, you tend to have the green line to be above the orange line. And this is because, for example, in 2005, a 5-year-old is more likely to live with their mother than a 15-year-old. So that's what you see here. And then, of course, as I mentioned before, these are lower bounds to actual fertility because you need the mother and the child to be living in the same household. So when you look at birth registries, you see a larger number. So this is what we expected to see. This is what we do see for 15 to 24-year-olds. Now let's do the same exercise for 10 to 14-year-olds. First, the line doesn't look that flat, but it may be actually changing in fertility rates. But once you bring in a census 10 years later, you see that we're actually recovering a much higher fertility. What's even more impressive is that we're recovering a number that is even higher than the birth records, the birth registries. So birth registries are normally thought as the gold standard for measuring fertility, and they are, but not for 10 to 14-year-olds, right? Where there's this strong incentive to hide the information. So now, if you put it side to side, you can see this difference in pattern. When we look at the 10 to 14, actually looking at 10 years later, you're going to recover something higher in both cases. And now let's see if this extends to more countries. And here we're going to do aggregating across the 80 census pairs that we have in IPUMS. And the idea is you take a census, and you're going to take the 5 years prior to the census for each age group. Thanks. For each age group and for each country. And then you're going to get also the subsequent census and get the estimate for each. So then you're going to compute the ratio between these birth counts for each country. You average them across countries, and then you get the figure that I'm going to show you next. And basically, when this number is positive, it means that you're getting a higher count in the latter census than in the earlier one. And this is the average across the 80 census pairs that we look at. And we see this individually in each census pair as well. And we see that this gap is declining as the mother, with the mother age at the time of childbirth. Okay, some other results, and I have been going a little bit fast, so then I will be able to show you a little bit of these. What happens if you could choose when to report? So in Mexican birth registries, there's some degree of choosing when to go and get the birth certificate. So what you see is when the mother is very young, it takes them more than 4 times the time to register the kid. So for example, for a 20-year-old, their kid is going to have a birth certificate within the first 10 months on average. But if the mother is 10 to 12, it's going to take on average more than 4 times to get a birth certificate. And this is going back to the social cost that we think decay with the mother's age at the time of reporting. And then we also see undercounting by misattribution. So when the numerator comes in, there are many ways of hiding the child. One is saying that there's no children or that the child is not in the household. You can also say that the mother is not in the household, or you could say that the mother is somebody else in the household. And for this mechanism, what you will see is the same way that we see missing births for 10 to 14, you should see excess births for old women. And that we do see nice evidence of. Is the average across countries. So the same, in a similar way that we're seeing missing births for 10 to 14 years old, we see excess births for 46 to 55-year-olds. So this is like consistent evidence with this misattribution. Ooh. Okay, and then for mechanisms, we try to think about if this is based on legal cost thing. It's based on legal cost or social cost. And what we do for legal cost is we leverage that many countries have minimum age of consent. So in many cases, these pregnancies and these births are evidence of a crime, right? Because these girls cannot even consent legally in many countries. So the idea is if there's legal costs, for example, going through the criminal process for the girl, or even retribution by the perpetrator, if there's all these legal costs involved, you will expect that before when this is not protected by the minimum age of consent, you should have less reported. You should have less reporting than when it's not protected by law. And what we see is no evidence of that. For all the countries where we have the date of birth by month, we see that there doesn't seem to be, the legal cost doesn't seem to be binding, but this is consistent with what we already know, that this type of crimes are often hidden, not reported, and so on. So to conclude, we claim that this is mostly driven by social costs that decay with the mother's age at the time of childbirth and with the mother's age at the time of reporting. We do some heterogeneity by countries by creating an index of women's agency, and we see that the undercounting is less in places where in countries where women have more agency. So to conclude, this paper documents systematic underreporting of child mother births. It's 20 to 30% in administrative records, up to 65% in census data. And a central role of this undercounting is due to the social costs that decay with mother age at childbirth and with mother age at reporting. And well, to conclude so these private reporting costs lead to lower data quality. So the idea is we need to find data collection alternatives that can align these private incentives with our goal of having good, high quality public goods. Thank you.